Today, we present our work, LipAT, Beyond Style Transfer for Controllable Neural Simulation of Lipstick. Simulating makeup on users' faces has broad interest in cosmetic industry, which helps to eliminate guesswork when shopping for makeup in online stores. We provide the problem statement as follows. We assume the images are captured in a handheld device in the wild with unknown lighting conditions. The data we have at hand is assumed to be unpaired face images of makeup and non-makeup. Paired data is expensive to collect. We focus on lipstick products and assume they can be characterized with roughness, color, and opacity values. Given these assumptions, we want to build a system that can augment a face image with a lipstick and its known attributes. The overview of our method consists of two main modules. The first, LipAT. This module takes as input an image without makeup and attributes of lipstick. LipAT leverages a PBR-like framework to perform makeup placement and render the lipstick attributes. Second, LipAT. The first module, LAM, may suffer from inaccuracies that stem from the face parser and diffuse and specular extraction. Therefore, this module refines the output of LAM while preserving the three attributes being the color, roughness, and opacity. The lipstick application module first decomposes the given image into its diffuse and specular components. Following that, it will update the specular component using the roughness score and the diffuse component using the base color of the lipstick. As the final step, the application module recomposes the output image using the updated specular and diffuse components and then updates the output using the lipstick opacity. Updating the diffuse component is performed using the following formulas, where LAB transforms the image from RGB color space to LAB color space. The mask M is a binary region of lip and is extracted using off-the-shelf library face mesh. In the image to the right, we can see the updated diffuse component using the given lipstick base color. The mask ensures the update is performed only on the lip region of the face. Previous works adopt either gamma correction on specular highlights or a PBR engine. The gamma correction-based techniques can produce highlights aligning with the specular highlights of the original images, but requires manually tuning of gamma for each image to produce realistic results. In contrast, rendering-based techniques need to estimate the lighting profile of the original image to produce realistic outputs. To bridge these two research gaps, our application module learns a conditional deep generative model that accepts the specular highlight component of the face image without lipstick and the roughness score of the lipstick, and returns the updated specular highlight component as the output. The objective function for training this network is composed of a PBR cost term and a gamma cost term. The PBR cost term leverages a synthetic dataset we have created, which simulates different lighting conditions and different roughness scores. To complement the PBR term, which might suffer from inaccuracies due to synthetic data not capturing all the real-world subtleties, and so we optimize a gamma cost term as well. The gamma cost term is optimized on real-world data using weakly unpaired information. We use the synthetic data to compute the X and Y parameters of the gamma correction component. Once the specular network is trained, it will update a given specular component of an image with the provided roughness score. Finally, composing the updated specular component with the updated diffuse component will be performed using the following formulas. The first performs screen blending composition, and the later incorporates the opacity attribute and the binary mask of the lip region. In the right image, we can see performance of our specular update. On the left image, we see the full process of the application module, showing the specular update, diffuse update, and the final composition. The output from the application module could be unrealistic for some examples due to two main reasons. First, incorrect placement of lipstick due to the imperfections in binary lip mask, particularly around the edge of the lip, and second, unrealistic specularities that are not well aligned with the input image. To address this, we introduced the refiner module, which has the objective is to refine the output of the application module and recover detail that was lost. The refiner module is composed of two networks. The first uses a pre-trained VGG19 network used to extract multi-scale features from both the input image and the output of the application module. The second module is a SPADE network, which enables modulation of pixel level and semantic level information through use of spatial adaptive normalization layers. We use both the input features and augmented features in a weighted fashion, such that the earlier layers weigh the original input features, and as the layers progress, we place more emphasis on the augmented features. We use 3 losses to train the refiner module. The first, called a cosmetic loss, which applies an L1 loss between the output and the augmented features. The second, refiner loss, is applied along the different multi-scale features similar to perceptual loss, though in addition we enforce the original image edges using Sobel filter. The final loss is the adversarial loss on the output, which draws real samples from the set of images with makeup. We next review the experiments we presented in our paper. In this work we used 4 datasets. 2 datasets were used for training and 2 for testing. The first training dataset consists of 10K images of unpaired makeup and non-makeup with lipstick attributes. For the unpaired makeup and non-makeup, we use Celeb A. For the lipstick attribute, we fitted a KDE over a large collection of lipstick information readily available online. The second training dataset is a synthetic dataset we created for training the specular network. It consists of paired tuples of specular component, roughness score, and updated specular component. We generated this dataset by using 80 faces, 25 lighting setups, and 5 roughness scores. The first test dataset is an unpaired subset of Celeb A that was not seen during training. The second test set is a weakly paired set of people with and without makeup, and the lipstick attributes corresponding to the sample with makeup. For more details on how this dataset was constructed, please refer to our supplementary material. The metrics we use to evaluate our approach are the structure similarity metric, L1 error, and a modification of the FID score, which we dub patch FID. For further details on the patch FID metric, which explain its derivation and differences from the standard FID metric, please refer to our supplementary material. Results for our approach across the various baselines can be seen in the following table. We test our approach against PBR baselines, neural style transfer baselines, and hybrid approaches, which we have modified NST approaches using our LAM component. The presented metrics in this table in fact correlate with different qualities in which users perceive accuracy. For example, the structure similarity metric correlates with preservation of the roughness attribute, while the patch FID correlates with users' judgment of what looks realistic. For more details and analysis of the conducted user study, please refer to our supplementary material. We now provide qualitative results for our approach. Here we show how specific attributes can be applied. In these examples we show smooth control of the attributes, indicating the framework has a continuous representation. Here we show comparison of our approach against the different baselines with the reference image without lipstick to the left, and another example of the same comparison. Thank you.